Hello, ladies and gentlemen. Welcome back. This is part 1 of chapter 7.2 with means, also known as expected value. Okay, we're going to be referring to expected value most of the time in this video. But remember, it's the same as an average. Mean, expected value, average. All right, so you can find this on page 483, and then I'm also going to go ahead and point it out on the formula sheet that is also right above this video on Schoology. All right, so to find the mean of a discrete random variable. All right, so here is our probability distribution. It's just the general form. We've got that x value on top. We've got the probabilities in the second row. All right, so what is this saying? All right, what is this saying right here? Well, that's telling us, ladies and gentlemen, to take the first x value and multiply it to the probability. And remember, we always use the decimal form. And then we're going to add it to the next x value times its probability. And we keep doing that until we get to the last x value and we multiply it to its probability. And so we will take a look at that in an example or two. Now, I want you to note this thing right here. Remember, this thing, ladies and gentlemen, is the summation symbol. And this is what you're going to see on your formula chart. Okay, so let me pull that up. You need to be familiar with this formula chart. And we will go over it quite a bit before the AP test, but let me show it to you here. So on the formula chart, okay, we did some of this stuff earlier, but if you go down, actually it's on the next page, my apologies. Right here on the second page of the formula chart, we've got our probability section. And you will notice, or you should recognize those. Those are the only two things they're going to give you for probability from chapter 6. Okay, so those are the two things they'll give you. Okay, the probability of A or B, and then the conditional probability. But this thing right here, ladies and gentlemen, that's our expected value. That is chapter 7.1, which we're looking at right now. Or I should say, sorry, 7.2, which we're looking at right now. All right, and this is also from chapter 7.2, but that's going to be in part 2. All right, so I'm going to talk about and use the expected value formula in part 1 video, and then I'll show you the variance and stuff in part 2. All right, at least I think it's in part 2. All right, let's keep going. All right, here we go. So the probability that a customer selects 1, 2, 3, 4, or 5 items at a convenience store are 0.32, 0.12, 0.23, 0.18, 0.15 respectively. First of all, is this a legitimate probability distribution? Well, first of all, are all of the probabilities between or from 0 to 1? Okay, I'm using E for an event. Okay, they are. Check. Do all the probabilities of the sample space equal 1? Well, let's find out. 0.32 plus 0.12 plus 0.23 plus 0.18 plus 0.15. Okay, if I add all of those up, I believe they do add up to 1. Yep, they do. So check. So yes, this is a legitimate probability distribution function. Remember, if you ever ask that question, you got to check those two conditions. Does it go from 0 to 1, and does it add up to 1? All right, so now the question is, when a customer comes into the store, what is the expected number of items he or she will buy? Okay, so we want to know the expected value. So this is what we're going to do, ladies and gentlemen. So We want to know what is the expected value. So we're going to take the one item. What's the probability of, okay, I've got the probabilities right here so I can look, I don't have to scroll up and down. The probability of buying one item is 0.32 plus the probability, or two items, the probability of buying two items is 0.12 plus three items, well, what's the probability of buying three items? 0.23 plus, there's no shortcut for this, folks. Okay, unfortunately, there's not. Four items, well, that would be times 0.18 because that's the probability of buying four items, plus five items, which is times 0.15. Now, again, there's no shortcut for this. Type that into your calculator, and we're going to end up getting 2.72 items. Now, I know you can't have part of an item, but we're just going to leave that as 2.72 items, okay? We're just going to leave that. So we don't want to round it to 3. So we expect, on average, we expect 2.72 items to be bought when a customer comes in. So they're going to buy somewhere between, we expect them to buy 2 to 3 items, closer to 3. Most of the time, they'll buy 3 items. But again, don't round it, leave the decimal like that. All right, pretty straightforward. Okay, let's look at this. If a player rolls 2 dice and gets a sum of 2 or 12, this person wins 20 bucks. If the person gets a 7, this person wins $5. The cost to play the game is $3. Find the expected payout for this game. Okay, so we want to know what is the expected value. So X in this case is the amount of money you expect to win, right? So let's think about this. We're going to start with 20 bucks. Okay, now what's the probability of rolling a sum of 2 or 12? Oh, the sum of 2 or 12. If you recall in an earlier lesson, we did all of those probabilities. Remember, there are 36 outcomes when rolling 2 dice. And a 2, how many ways can you roll a 2? Well, there's only 2 ways, or 1 way, sorry. There's only 1 way you can roll a 2. How many ways can you roll a 12? Well, ladies and gentlemen, that means both dice would have 6 dots on it, right? So there's only 1 way to roll a 12. So the probability of rolling a sum of 2 or 12 is 2 out of 36. Now, if you want to reduce that, you certainly can, but it's not necessary. Okay, so that's winning 20 bucks. Plus, okay, well, the person might win 5 bucks. Well, what's the probability of winning 5 bucks? Well, if you remember, rolling a 7, there's 6 ways that that can happen. So 6 out of 36. Plus, you don't win any money. Now, this one's not necessary, but I'm going to stick it on there anyway. So your chance of not winning would be the rest of them, right? So that would be, let's see, that uses 8 out of 36. So that would be what, 28 out of 36? Now, again, that one is not necessary because 0 times anything is 0. So you could technically leave that off. All right, now, if I punch that into the calculator, ladies and gentlemen, I'm going to get $1.94. That is the expected payout. Okay. That is the expected payout. It costs $3 to play the game. Okay, it costs $3 to play the game. So, in the long run, the person running this game keeps how much? So, if it costs $3, and for every $3 that is played, they expect to pay out $1.94. Okay, well, how much does that leave? That only leaves, or that leaves $1.06. Okay, I think I did my math correct there, right? $1.06. That means, ladies and gentlemen, that the person running this game keeps $1.06 for in the long run. Okay, it's guaranteed. In the long run, this person, game of chance, fair game, they're going to keep $1.06 of every $3 given to them. Not bad. Okay, so if lots of people play this game, you're going to make some money. Remember, casinos, you never have more than a 50% chance of winning. Casinos always have more than a 50% chance of winning. Okay, remember that, because in the long run, they're going to win. Okay, now here's another one. Most states, this is on example 7.5, page 482. Most states and Canada provinces have government-sponsored lotteries. Here is a simple lottery wager from the Tri-State Pick 3 game that the New Hampshire shares with Maine and Vermont. You choose a 3-digit number. The state chooses a 3-digit winning number at random and pays $500 if your number is chosen. Because there are 100 3-digit numbers, you have a probability of 1 out of 1,000 chance of winning. Okay, where did they get the 1,000 from? 10 digits times 10 digits times 10 digits, that's 1,000. Okay, there's 1,000 different numbers, and they have to choose your number, which there's only one possibility. So you have a 1 out of 1,000 chance of winning. Okay, so this is what it looks like. $0 is chance of that is 0.999, right? Okay, 1 out of 1,000, folks, 1 out of 1,000 is 0.001. So that means 999 out of 1,000 is your chance of losing, which is 0.999. Okay, what is your average payoff from many tickets? Now again, you don't have to use the 0, but I'm going to go ahead and do that anyway. So I'm going to take, so my expected payout is 0 times the 0.999 plus the 500 times the 0.001. Now again, that multiplying by the 0 does not mean anything. You don't have to do that. All right, so now you take your handy dandy calculator and you take 500 times 0.001, and ladies and gentlemen, wow, it's 50 cents. 50 cents. 50 cents. On average, they're going to pay out 50 cents. So if a ticket costs $1, in the long run, how much does the state keep? Well, for every dollar the state gets, they are going to pay out 50 cents. So, ladies and gentlemen, the state keeps the other 50 cents. All right. Pretty cool, huh? Okay, here's something you really need to know. Boy, put a star by this thing. Okay, law of large numbers. You really need to understand this concept. Draw independent observations at random from any population with finite mean mu. Decide how accurately you would like to estimate the mean. As the number of observations drawn increases, the mean x bar of the observed value eventually approaches the true mean of the population as closely as you specified and stays that close. Okay, let's take a look. Example 7.8 on page 488. Heights of women. The distribution of the heights of all women is close to the normal distribution with mean 64.5 inches and a standard deviation of 2.5 inches. Suppose that the mean 64.5 were exactly true. Figure 710 shows the behavior of the mean height x bar of n women chosen at random from a population whose height follows. Remember this notation, folks. Capital N means normal, approximately normal. The first number is the mean, the second number is the standard deviation. The graph plots the value x as we add women to our sample. Okay, the first woman drawn had a height of 64.21. So the line starts there. The second height, 64.35 inches. So for n equals 2, the mean is, so they took those two means and they averaged them. This is the second point on the line in the graph. Okay, so here's what the graph looks like. So they started off, it's almost like the coin flip. Remember the coin flip? Okay, it does the exact same thing. Eventually the mean, when your samples are large enough, it will level off at where the true mean is. Again, using random samples. All right? Think about the law of large numbers, page 489. The law of large numbers says broadly that the average results of many independent observations are stable and predictable. The gamblers in a casino may win or lose, but the casino will win in the long run because the law of large numbers says what the average outcome of many thousands of bets will be. An insurance company decides how much to charge for life insurance, and the fast food restaurant decides how many beef patties to prepare, also rely on the fact that the averaging over many individuals produce a stable result. It is worth the effort to think about more closely about so important a fact. Okay, page 490, example 7.9. The hot hand in basketball. No, law of small numbers. Okay. Belief in the law of small numbers influences behavior. Again, let me repeat that. Belief in the law of small numbers influences behavior. If a basketball player makes several consecutive shots, both the fans and her teammates believe that she has a hot hand and is more likely to make the next shot. This is doubtful. Careful study suggests that runs of baskets made or missed are not more frequent in basketball than would be expected if each shot were independent of the player's previous shot. Baskets made or missed are just like heads and tails in tossing a coin. Of course, some players make 30% of their shots in the long run and others make 50%, so a coin toss may not be the best model for basketball shots. Our perception of hot or cold streaks simply show that we don't perceive random behavior very well. Gamblers often follow the hot hand theory, betting that a run will continue at other times. However, they draw the opposite conclusion when confronted with a run of outcomes. If a coin gives 10 straight heads, some gamblers feel that it must produce some extra tails to get back to the average of half heads, half tails. Not so. Okay, read that part to yourself. If the next 10,000 tosses gives about 50% tails, those 10 straight heads will be swapped by the later thousands of heads and tails. No compensation is needed to get back to the average in the long run. Remember that it is only in the long run that the regularity described by probability and the law of large numbers takes over. Caution. Our intuition doesn't do a good job of distinguishing random behavior from systematic influences. This is also true when we look at data. We need statistical inference to supplement exploratory analysis of data because probability calculations can help verify that what we see in the data is more than random patterns. Okay, how large is a large number? Page 490. The law of large numbers says that the actual mean outcome of many trials gets close to the distribution mean mu as more trials are made. It doesn't say how many trials are needed to guarantee a mean outcome close to mu. That depends on the variability of the random outcome. The more variable the outcomes, the more trials are needed to ensure that the mean outcome X bar is close to the distribution mean mu. Casinos understand this. The outcomes of games of chance are variable enough to hold the interest of the gambler. Only the casino plays often enough to rely on the law of large numbers. Gamblers get entertainment. The casino has business. Okay, the law of small numbers. I want you to go read about that on page 489. Okay, law of small numbers. All right. I had said earlier that we weren't going to look at variance, but we are going to look at variance. Okay, so on the formula chart, we're going to do this now. So this is still part one in the video. So here we go. So variance. If you remember, ladies and gentlemen, this is the standard deviation, right? Standard deviation. The standard deviation squared is called the variance. The standard deviation squared is called the variance. So if you take the variance and the square root, you get the standard deviation. Okay, so please realize the variance is the square of the standard deviation. So how do you find it with this information? Okay, well, this thing right here, it looks really complicated, but it's not that bad. All right. It'll make more sense when we look at the example. I'm not going to write all of that out. And this right here, ladies and gentlemen, that's what you see on the formula chart. See, right here. So this is the variance. Okay, so let's look at an example. It'll make a lot more sense. Here we go. Here's our problem that we did earlier. The probability of selecting a customer selects 1, 2, 3, 4, or 5 items at a convenience store is, okay, those probabilities. And from the previous problem, we found that the mean is 2.72 items. Okie doke. Now we're going to find the variance. Okay, here we go. To find the variance, ladies and gentlemen, we are going to take the X value, which is one item, minus the mean squared times its probability. Okay? That's the one item. One item minus the mean squared times its probability, plus 2 items minus the mean, or the expected value, sorry, let me use the word expected value, squared times its probability. Plus, and again, there's no shortcut. You can't type this into anywhere on the calculator and it's going to spit out the answer. You have to actually go type this whole thing in. Okay, this is one of the few times where the calculator doesn't shorten it up very much. All right, now we're going to do 3 items minus 2.72 squared times 0.23, because that's the third one, plus 4 items minus the expected value squared times its probability, 0.18, plus 5 items minus the 2.72 squared times its probability. Okay, no shortcuts. So yes, ladies and gentlemen, you're going to have to do this. You're going to have to go parentheses 1 minus 2.72, close it, squared, times, let's see, what is it again? 0.32. Close it, plus parentheses. Okay, I'm not going to do this the whole way. 2 minus, all right? So yes, you got to type it in all like that on your calculator and hope you don't mess up. And so what we end up with here, ladies and gentlemen, is 2.1016. Okay, that's the variance. Okay, that's the variance. So if I go one step further, ladies and gentlemen, and I find the standard deviation, okay, the standard deviation, I simply take the square root of that variance. And so I take the square root of 2.1016, and I get 1.45. And that is the standard deviation of this situation. Now, let's see if we can remember what this is telling us. Okay, so let me do this. So remember our normal curve, ladies and gentlemen. Okay, the average number of items is 2.72, right? 3 above, 3 below. Okay, now let's think about this. The standard deviation is 1.45. So if I add 1.45, that would be one standard deviation above the mean. If I subtract 1.45, that would be 1.27 items. Now remember, this is the number of items that a customer is buying. So remember your 68, 95, 99.7% rule, the empirical rule. So this is telling us, ladies and gentlemen, that 68% of the customers that come into the store are going to buy 1.27 to a little over 4 items. Okay, and then you remember 2 standard deviations is the 95%, and 3 standard deviations is the 99.7%. Now, this doesn't work very well going to the other stuff because we end up with negatives, and really you can't have negative numbers. So, but I want to remind you of what the mean and the standard deviation can tell us if it's approximately normal. All right. Oh, and I already did that. So again, the standard deviation is the square root of the variance. So that's the square root of the 2.1016, and we got 1.45. All right, I think, yep, that was it, folks. Okay, we will talk in the next video, we will talk about the rules for means, variances, and standard deviation. Okay, so there are some rules that go along with that. All right, hopefully all of that was pretty easy. It's pretty straightforward. It's doing some real math finally with calculations and using probability. All right, folks, good luck. I will see you soon.